day 14, machine learning. The little machine that wanted to learn. We need to start the machine first, and then we can read on. So the CTO has made our toy pipeline go wrong by infecting the elves at key positions in the toy making process. He's poisoned the pipeline and caused the elves to make defective toys. McSkiddy has started to combat the problem by placing control elves in the pipeline. These elves make measurements of the toys and try to narrow down the exact location of the problematic elves in the pipeline by comparing the measurements to the defective and perfect toys. However, this is an incredibly tedious and lengthy process, so she's looking to use machine learning to optimize it. So we're going to learn what is machine learning, basic machine learning structures and algorithms. And we're going to use a neural network to predict defective toys. Before moving forward with today's lab, you need to connect to a VM. And there's a split screen, so we don't have to worry about any attack boxes today. To access the machine that we're going to work on, click the Start Machine button, wait 3 minutes, and it will open on the right-hand side. So over the last decade, there's been a massive boom in artificial intelligence and machine learning systems. Just in the last couple of years, the release of ChatGPT has taken the world by storm. However, these systems how these systems actually work is often shrouded in mystery, leading to a lot of snake oil sales tactics. In this task, we'll provide you with a glimpse into the world of ML and help demystify the incredibly interesting topic. We'll create our very own neural network that can be used to detect defective toys. 0 to hero on artificial intelligence. Before we can create our own AI, we need to learn some of the basics. First of all, let's discuss the two terms. The term AI is used in broad strokes out there in the world, often incorrectly. We have to be honest with ourselves. AI can't just be a bunch of if statements. A better term is to use machine learning. Machine learning refers to the process used to create a system that can mimic the behavior we see in real life. This is because there is intelligence in real life and its structures. The field is incredibly broad, but here's a couple of popular examples. We have genetic algorithms. This machine learning structure aims to mimic the process of natural selection and evolution by using rounds of offsprings and mutations based on the criteria provided. The structure then aims to create the strongest children through survival of the fittest. A particle swarm. So this machine learning structure aims to mimic the process of how birds flock and group together at specific points. By creating a swarm of particles, the structure aims to move all particles to the optimal answers grouping point. And neural networks. So the machine learning structure that is by far the most popular aims to mimic the process of how neurons work in the brain. These neurons receive various inputs and are then transformed before being sent to the next neuron. These neurons can then be trained to perform the correct transformations to provide the correct final answer. There are many more machine learning structures, but we'll stick to neural networks for this task as they are the most popular, and while there's a significant amount of maths involved in implementing a machine learning structure, we'll be abstracting this information. If you want to learn more, you can start here. This is a book. This is where I started, and then work your way up. I wonder if they've got yeah, there you go, for a book. Neural networks for babies. Nice. On our list of machine learning basics to cover, this neural network's language style. In order to train our neural network, we need to decide how we're going to teach it. While there are different styles and subsets of styles, we'll only focus on the first two of the main styles for now. Supervised learning. In this style, that will guide the neural network to the answers that we want it to provide. We'll ask the network to give us an answer and then provide it with feedback on how close it was to the correct answer. In this way, we're going to supervise the neural network as it learns. However, to use the learning style, we need a dataset where we should know the correct answers. This is called a labeled dataset, as we have a label for what the correct answer should be given the impact. This is what I did for the number plate recognition, if you watch those streams. So, unsupervised learning. This is the learning style that will take a bit more of a hands-off approach and let the neural network do its own thing. While this sounds strange, the main goal is to have the neural network identify interesting things. Humans are quite good at most classification tasks, for example, simply looking at an image and being able to tell what colour it is. But if someone were to ask you why is it that colour, you would have a hard time explaining the reason. Humans can see up to 3 dimensions, whereas neural networks have the ability to work in far greater dimensions to see patterns. Unsupervised learning is often used to allow neural networks to learn interesting features that humans can't comprehend and can then be used for classification. A very popular example of this is the restricted Boltzmann machine. Have a look here at this weird feature, and the neural networks learned to classify different digits. So here's like a set of numbers, and the machine has to guess what the numbers are. And there's a lot of maths. For this task, we'll focus on the supervised learning. It's an easier learning style for the learning the basics, including the basic network structure. Next on our list of machine learning basics to learn is the basic structure of a neural network. Sticking to the very basics of machine learning, a neural network consists of various different nodes or neurons, and then these are connected as shown in the animation below. So you feed it height, width, length, color scheme, maker RFID, checker RFID. Then each of those neurons connect to, a hidden node. They're all interconnected, and then those are hidden interconnected with those, and there could be many more than just 2. So, as shown in the animation, the neural network has 3 main layers. The input layer, this is the first layer of nodes in the neural network. These nodes each receive a single data input that is then passed on to a hidden layer. This means that the number of nodes in this layer always matches the machine's number of inputs. For example, if our network takes a toy's length, width, and height, there are 3 nodes available in the input layer. The output layer, this is the last layer of the node in the neural network. These nodes send the output from the network once it's been received from the hidden layers. Therefore, the number of nodes in this layer will always be the same as the network's number of outputs. For example, if our network outputs whether or not the toy is defective, we will have 1 node in the output layer for either defective or not defective. We could also do this with 2 nodes, but we won't go into this here. And the hidden layer. This is the hidden layer of nodes between the neural network's input and output layers. With a simple neural network, this will only be 1 layer of nodes. However, for additional learning opportunities, we can add more layers and create a deep neural network. This layer is where the neural network's main action takes place. Each node within the neural network's hidden layer receives multiple inputs from the nodes in the previous layer, and then this transmits their answers to multiple nodes in the following layer. Now that we understand the basic layout of the neural network, let's zoom in on one of the nodes in the hidden layer and see what's actually going on. As mentioned before, we'll simplify the maths quite a bit here. In essence, the node is receiving an input from nodes in the previous layer, adding them together and then sending the output onto the next layer of nodes. There is, however, a bit more detail in this step that's important to note. Inputs are not directly added, instead they are multiplied by a weight value first. This helps the neural network decide which input should contribute more to the output than the others. In addition to output, the addition's output is not directly transmitted out. Instead, the output is first entered into what is called an activation function. In essence, this decides if the neuron node will be active or not. It does this by ensuring that the output, no matter where the input, will always be a decimal between 0 and 1, or between -1 and 1. Now that we understand the neural network structure, how layers and nodes within it work, let's dive into how the network is trained. There are 2 steps to training the network, the feed-forward step and the back-propagation step. The feed-forward loop is how we send data through the network and get an answer on the other side. Once our network has been trained, this is the only step that we perform. At this point, we stop training and simply want an answer from the network. To complete 1 round of the feed-forward step, we have to perform the following. We normalize all the inputs and allow the neural network to decide which inputs are the most important in helping it to decide the answer. We need to normalize them. As mentioned before, each node in the network tries to keep its answer between 0 and 1. If we have one input with a range of 0 to 50 and another with a range of 0 to 2, our network won't be able to properly consume the input. Therefore, we normalize the inputs first by adjusting them so that all their ranges are the same. In our example here, we would take the inputs with a range of 0 to 50, divide them all by 25 to change their input ranges from 0 to 2. So is it showing that in this bit? No, it's just lightning bolts. Okay, right, and then we feed the input into our node in the input layer. Once normalized, we can provide one data entry for each input node in our network. We'll propagate the data through the network. At each node, we'll add all the inputs and run them through the activation function to get the node's output. This output then becomes the input of the next layer of nodes, and we repeat this process until we get to our network's output layer. Read the output from the network, so at the output layer, we'll receive the output from our nodes. This answer is a decimal between 0 and 1, but for decision making, we'll round it to get a binary answer for each output node. And then backpropagation. This is where we're training our network to feed. The feed-forward loop is only half the process. Once we receive the answer from the network, we tell it how close it was to the original answer, the correct answer. This is the backpropagation step. Here we perform the following steps. We calculate the difference in received outputs versus expected outputs. As mentioned before, the activation function will provide a decimal answer between 0 and 1. Since we know the answer has to be either 0 or 1, we can calculate the difference in the answer. This difference tells us how close the neural network was to the correct answer. We can then update the weights of the nodes, and using the difference calculated in the previous step, we can start to calculate the weights of each input to the nodes in the output layer. We won't dive too deep into this process as it often involves a lot of complex maths to decide what updates should be made. And then we'll propagate the difference back to the other layers, and this is where the term backpropagation comes in. Once the weights of the nodes have been updated, we can calculate the difference would be for the previous nodes. Once again, this difference is then used to update the weights of the nodes in that layer before being propagated backwards even further, and we'll continue the process of backpropagation until the weights for the input layer have been updated. Once all the weights have been updated, we can run another sample of the data through the network, and we repeat this process with all our samples in order to train the network. Right, dataset splits. The last topic to cover before you can build our network is a data split set. A dataset split. I can't fucking read today. Let me take this off too. Hey Dylan, how's it going? Right, so dataset splits. Let's use an analogy to explain this. Say your teacher constantly tells you that 1 plus 1 equals 2 and 2 plus 2 is 4. But in the exam, your teacher asks you to calculate 3 plus 3.
Doing good.
Good to hear. 3-streak stream, nice. So your teacher asks you to calculate 3 plus 3. The question here is, have you just learned what the answer is, or did you learn the fundamental principle required to get the answer? In short, you can overtrain yourself by learning the answers instead of learning the required principle itself. The same thing can happen with the neural network. Overtraining is a big problem with neural networks. We're training them with data where we know the answers, so it's possible for the network to simply learn the answers, not how to calculate the answer. To combat this, we need to validate that the neural network is learning the process and not the answers. This validation also tells us that we need to stop our learning process. To perform this validation, we split our dataset into 3 datasets below. We've got the training data. This is our largest dataset. We'll use it to train the network, usually about 70 to 80% of the original dataset. The validation data, this is used to validate the network's training. After each training round, we send this data through the network to determine its performance. If the performance starts to decline, we know that we're starting to overtrain and we should stop the process. Usually this is about 10 to 15% of the original dataset. And testing data. So this dataset is used to calculate the final performance of the network, and the network won't see this dataset at all until we're done with the training process. Once the training is complete, we'll send this through the testing dataset to determine the performance of the network. Usually, again, this is about 10 to 15% of the original dataset. So now you know the basic neural network works, let's build our own. So putting it all together, now that we've covered the basics, we're ready to build our own neural network. Start the machine in the top right corner and it will show you the split screen after 2 minutes. You can find the files that you're working with on the desktop in the neural network folder. You're provided with the following files. So let's open new. So we've got detector.py. This is the script where we'll build our neural network. Some sections have already been completed. We've got dataset train. This is the training dataset. The elves have not only captured the measurements of the toy's view, but whether the toy was defective or not. We'll use this dataset to train, validate, and test our neural network model. And then data ESET, or EST set. So this is your testing dataset. The elves have only captured the measurements of the toys, and due to the sheer volume of the toy pipeline, we're unable to determine if the toy was defective or not. Once we've trained the neural network, we'll predict which of the entries in the file are defective for McSkiddy to remove from the pipeline. Our first step is to complete the detector.py script. Let's work through the initial code. It's already been added for you in the script as shown in the snippet below. So make you big. So these imports are what we need for the neural network. NumPy is a powerful array matrix. This is what we used in like day one. We used Pandas, didn't we? So Pandas is the data processing library. Also allows for reading and formatting data structures. Then sklearn is model selection. This is used for splitting the data. Then we're going to use this to normalize the data, so the standard scalar. And we're going to encode the text data to integers using a label encoder. We're going to have a multi-layer perception neural network. So we've got a classifier. And then these are the color labels that will convert to integers. So red 0, 1, 2, 3, so on. Read the training and testing data files, so we'll pull in the data. And then the neural network cannot take strings as input, therefore we encode all the strings as integers, so that's what the label encoder is doing. And then we read our training data from the CSV file, and we'll read the data we'll train on, and then once we've read the labels of the training data, and then we can read the testing data. So let's work through what the code does. The first few lines are purely imports that we'll need for the neural network to function. We'll make use of Pandas and read our dataset, and the scikit-learn for building the network. Next we'll load the datasets, in our case the training and testing dataset, and we pull in the labels as well, or you don't, and then we'll perform a supervised learning, which only know our network's true performance once we've uploaded our predictions for review. Once the data is loaded, we'll need to make sure that the inputs are numerical values. One of our data types is the toy's color scheme. In order to provide the data with our network, we'll encode all the colors to numbers. Lastly, we'll load the data variable X and use it to store our training data set together with the labels stored in Y, and then we'll test whether the stores lastly, test X stores the data set that we'll use to perform predictions on. So now that we'll start to add the code required to build and train the neural network, we'll do this in the steps perform actions mentioned above. We'll create the data sets. So where's our code? There we go, so we need to edit here. Got any other editors? It's not. I don't like the purple on black, like it's not very readable. They had Sublime text, I think, on the other one. Oh well, whatever. We'll deal with it. Right, so to do this we have to add the following line to our code after the insert dataset split code. So train X, validate X, train Y, validate Y, that equals train test split X, Y, test size equals 0.2. And this splits our training data into two. We'll get these variables filled. And that contains, so Y has labels, X has the data, normalizing the data. So next we need to normalize the data. We can do this by adding the following lines in our code after the insert normalization. Let's do this properly. So scalar equals scalar, standard scalar. Scalar dot fit train X. Train X equals scalar dot transform train X. Validate X equals scalar dot transform validate X, see, and test X equals.
Irasakai says, Magoo.
Hey,
Translated
Nick.
from Spanish.
What's cracking?
Translated from Tagalog.
I do need to get good at typing, apparently. Right, so as you can see, the lines of code, we cannot cheat by determining the normalization on either the validation or test datasets. Normalization vector is only created from the training data, which is applied to all three datasets. Training the network. Finally, we can train our network, and we need to create our classifier with the following code. So here, so CLF equals the MLP classifier, and we're going to solver equals LBFGS alpha equals 1E minus 5. Hidden layer sizes. This takes tuple 15.2. And then max iter equals 10,000. So you can find more information on the specific classifier here. So the MPL classifier, multi-layer perception classifier. This model optimizes the log loss function using LBFGS, or the stochastic gradient descent. I'm not even going to pretend what any of those fucking mean. This is a bit of explanation as to what the values are doing. So solver, this is the algorithm used to update the weights. This is the classic back propagation algorithm, but others can be used as well. Alpha is the value used for the regularization of the neural network. We won't dive too deep into the maths here, but we've selected a fairly default value. And the hidden layer sizes, this tells us the structure of the hidden layers in our neural network. Based on the provided configurations, we have 2 hidden layers and 15 nodes in each layer. And then max iteration. This is a cap on the number of iterations that we'll train the network for before it's stopped. Next, we can train the classifier on the following code. So this is going there. So clf.fit train x, train y. When this step is complete, we've successfully trained the neural network. And then the validation step. So this step is to validate our neural network, and to do this we can ask the network to predict the values based on the validation dataset. Y predicted equals clf.predict validate. As you'll see, when you execute the script, predictions are significantly faster than the training the network. This is why the neural network can be actually used in real-life applications, as the prediction rate is incredibly fast once the network has been trained. We can determine the accuracy of our classifier by comparing the 2 arrays with the following code. So that's already done. And then we do here y underscore test prediction equals clf.predict test x. Cool, and then that's it, and then we're finally ready to train the network from the terminal, run the application. So let's save everything. Open the terminal. Python 3 detector.py. Fingers crossed I wrote it correctly. Apparently I didn't. So what did I fuck up? Text. Oh, test X, not text. So no, I got it there. What's it on about? Let's have a look. Trainer. Test X. Test X. Let's try again. That's better. Oh no, fuck something else up. MLP classifier was not defined. Is it there? Should it be? MLP class. Just an I. Okay. So it's starting training. Just thinking about it. TryHackMe servers are on fire right now. Spinning up all the extra instances to get this to run. Oh, damn it. What else did I miss? Has no attribute predict.
Not Richie says.
Oh wow, they're teaching machine learning on THM. Wild.
Yeah. And it's on the advent of cyber stuff. Predict. Train X, train Y, predict. That's what I put. So. Oh, here, predict. Twat. Yeah, this room's like it's really wordy, but there's good explanations. They've linked to like all the scikit. Where was the other? There we go. So the classifier's linked as well. So you could go down some pretty good rabbit holes here. So, trains iteratively since each step of the partial derivatives. Derivatives of the loss function with respect to the model parameters are computed to update the parameters. Oh, what are you on about? It would be nice if they actually include an IDE in this so it shows that you've fucked up when you've copied stuff. So what was it moaning about? Didn't like wide test predictions. So I called it prediction. Okay. Good for debugging at least. Gets you in the habit of reading code and seeing what you did wrong. Right, so yeah, these predictions will be saved to a file and upload. You can then upload your predictions here to see how well the neural network performed. If your accuracy is above 90%, you'll be awarded the flag. Can't reach that, so I need to do it in the VM. So, link. Let's open Firefox while it's doing the training. Should we all go get a cup of tea while we wait? Here we go.
Irasakai says. Dick. Translated from Dutch.
So where does it save it? We've got saving the predictions. I'm guessing it's that text file then.
I do say Dick.
Yeah, it wasn't a translation at all. Right. Neural network prediction. Upload. Aha! That's the last one. What was the other ones that we didn't do? What was the other term given for the artificial intelligence, the subset of AI meant to teach computers how to think, how nature works? That was the evolution one. I can't remember the name already. I've already forgotten.
Christy says, Hello 07, lurk smile
Hello.
smile.
Genetic algorithm. No. Was it the neural network one? Supervised?
Not Richie says,
E Christie?
translated from German.
So actually, genetic algorithms, that one. There we go. And then learning style that makes use of labeled data. Structured learning.
Christy says, Hey go pro sloyo, soars and walking dog, D. Not Richie says,
Dois pontos do Gelurk.
translated from Indonesian.
Deutschlurk.
Msek says, Msek Doge, translated from Tagalog. Lodikin says, Yay for 8 ads.
Yeah, and watch them all. Okay, helps if I spell it right. Other term for artificial intelligence, or the subset of AI used to teach computers how we... machine learning. Duh. What's the name of the layer between the input and output layers of the neural network? That's the hidden layer. What is the name of the process used to provide feedback to the neural network on how close its prediction was? That was feedback process, but I've got no idea what hyphen they want in it. Back propagation. There we go. If you enjoyed the room, we invite you to join our Discord for ongoing support. I bet their Discord blew up yesterday. Like, what the hell is ML? Terminate blocks. I quite like using this for doing the visuals on the web app that I was building. So this does classification of objects, so you can just point an image and it will classify the image for you to tell you what objects are in the scene, which is pretty sick. There's Yolo V8 saying what's have a play.
Web link.
And then to train it, you can actually use like these to train your own one. So so I used the base one to do car detection, and then had another one that we got off, I think it was RoboFlow. No, it's not. There's another one anyway that let's see if I can find it, that has like a load of pre-classified things on it. Lessons played. Oh, it was RoboFlow. There you go. This is the. Then this is what we use for the license plate detection. So they give you a sample data set. It's all foreign, so I had to like completely delete it and make another one for GB number plates. And then this doesn't come pre-trained. You've got to train it yourself. But you can use one of these options to train it. Yeah, pretty good.